Kelly was running a seminar. I told you about the seminar in which the students were dummy and stupid and so forth and so on. But he was running the seminar, and one day he came into class, and when he didn't say theorem, he said cherim, and I told you he talked with his teeth clenched like this. We got to prove these chirims. And he came into class one day and into the seminar, and he said, we're just not getting enough work done in here. We're going to have to start meeting on Sundays. And there was dead quiet in there, and this boy raised his hand. And Porcelli looked at him and he said, yes. He said, Professor Porcelli? Said, I go to church on Sunday. And Porcelli walked over to him like this. Well, he wasn't walking with a cane, but he walked over to him like this, and he got right up to him and he said, did you come here to study mathematics or religion? So I'll turn it over to Carl. His last talk in the Porcelli series this time is on smooth numbers. Is that correct? Smooth
Yes.
numbers.
Thank you very much. I've enjoyed very much giving these lectures, and I appreciate all of you coming to these lectures. I know it's difficult to listen to a lecture outside of your own field, and especially 3 days running. So thank you. The title of my talk today is Smooth Numbers, and the first question you might wonder is, what am I talking about? What is a smooth number? Well, actually, it doesn't have a tremendously long history as a term. The term was coined by Ron Rivest, who is a computer scientist at MIT, about 20 years ago. And he didn't mean anything deeply profound by the name smooth number. A smooth number is a number all of whose primes are small. So we say n is y smooth if all of the prime factors of n are less than or equal to y. So for example, if you were to look at a two smooth number, not TOO, but TWO, smooth number, it would be essentially a power of 2. Nothing more than that. And if you looked at a three smooth number, you'd be looking at a number that's either a power of 2 or a power of 2 times a power of 3. And so on. The concept has been around forever, of course, to have a number with all small primes. And they've been useful in number theory for almost all of the century. For example, the Soviet number theorist Vinogradov proved some very interesting theorems using the concept of smooth numbers, and we'll see more about the earlier history of these long before Ron Rivest coined the name. A number theorist in Canada, but maybe you know him, his name is Ram Murthy, thought the name smooth was interesting. He wanted to know what do you call a number that's not smooth? In other words, a number which has a large prime factor. And so he invented a name for that in analogy to peanut butter. So such a number with a large prime factor is called crunchy, according to him. But somehow or other that name hasn't stuck yet. Maybe to the roof of your mouth it is stuck, but other than that. Okay. Let's get a feel for these things. There's another word or notation that's common here. We have psi xy is where you count how many y-smooth numbers there are up to x. So this is equal to the number of y-smooth numbers that are less than or equal to x. So for example, suppose we try to count this, try to figure out what this number is, psi 110. So what we'd like to know is how many numbers there are up to 100, all of whose prime factors are less than or equal to 10. In other words, we're only allowed to use 2, 3, 5, and 7 in the prime factorization. So it turns out that this number is 46, and this afternoon I worked out two different ways to count this. So the first way would be the direct way, where we actually construct the smooth numbers. So the direct way might be you start with the powers of 2. Okay? So you count the powers of 2 up to 100. Well, they go up to 2 to the 6th. And if I include 2 to the 0, which is 1, then there are 7 of them. And then I can say, okay, how about 3 times the power of 2? So for the 3's, well, I'll have 3 times the power of 2, so it'd be 3 times the number less than or equal to 33. And so I'd get 6 for that, because 32 is 2 to the 5th. And then I'd get 9 times the number less than or equal to 11. Okay, so I get 4 for that, because 2 to 8 is 2 cubed, just below 11. And then 27 times the number less than or equal to 3, so there are 2 for that, 1 and 2. And 81 is 1 more. So here, if I just stopped here and I added up these numbers, I'd have the number of 3 smooth numbers up to 100. And now what if I do the 5's? They're a little harder. So first of all, I have 5 times the number less than or equal to 20, which is 3 smooth. Or maybe, why don't I do it this way? I say it's 20 and subtract off the numbers that aren't 5 smooth, less than or equal to 20. How many numbers less than or equal to 20 aren't 5 smooth? Those would be 7 and 14. That's 2. 11, 13, 17, and 19. That's 6. So I take away 6. So there are 14 numbers that are 5 smooth and whose largest prime factor is 5. And then I can do the 7's. And so then I'm just counting up to 14, because 14 times 7 is 98. And so I have 14 take away 2, which is 12. And so if I add up all these numbers, I ought to get 46 if I did it right. This number is 13. So that's 20. I guess I did it right. That's 46. Now there's a second way to do it that's sort of similar to the way I did these 5's and 7's. And that's just to count the numbers up to 100 that are not 10 smooth and subtract. Okay? That's the other way of doing it. So let's do that. So I could take 100, and now maybe it's not 10 smooth because there's a prime factor between 50 and 100. Okay? There are 10 of those. There are 10 primes between 50 and 100. Now, what about primes between 33 and 50? So those are the primes 37, 41, 43, and 40. There are 4 of those. So I have the 4 of those and their doubles. So it's minus 4 times 2. And now to take the primes between 25 and 33. There are 2 of those, 29 and 31. So those 2 primes, they're doubles and they're triples. So for those 2 primes, I take away 3 each for them. Now I consider primes between 20 and 25. Just one of them, 23. And I'll take away 4 for that because I have 23, 2 times 23, 3 times 23, and 4 times 23 to kick out. And now let's just do individual primes now. I guess we're down to the smaller primes. 19, how many multiples of 19 do I kick out? Seems like I'll kick out 5 of them, up to 5 times 19. And how about for 17? Well, I also kick out 5 of them because 6 times 17 is already too big. And how about 13? Well, I'll kick out 7 multiples of 13. And how about 11? I'll kick out 9 of those. And if I work this out, this should also work out to 46. Okay? So this is sort of boring, just looking at all these small numbers here. Let's try to generalize this issue here of 110. And let's generalize it as follows. What is psi x to the 1/2? How big do you think that is? Now, we can try to estimate this by counting. The first way is too complicated. The second way is a lot simpler. Let's try to count this the second way. But for each of those primes, we have to take away how many multiples they have. Like if the prime was between 50 and 100, I just had to take away the prime. But if the prime was like between 33 and 50, I had the prime and the double of the prime to take away. So the idea is exactly what you say. Let's say I just take x, start with all the numbers up to x, and then subtract off for each prime that's bigger than the square root of x and less than or equal to x. I'll subtract off how many multiples it has. So I'm going to subtract off 1 times p, 2 times p, 3 times p, up to k times p, where k is as big as possible. K is the integer part of x over p. So this is essentially an exact formula for the number of x to the 1/2 smooth numbers up to x, and except it's exact if x is an integer. And let's now try to estimate this by removing the integer part sign. And if I remove the integer part sign, I'll make an error in doing so. And the error that I make is at most 1 for each term in the sum. And the number of terms in the sum is the number of primes there are in this interval. And the number of primes in this interval is order x over log x, which you can see is smaller compared to already this term here. And so to estimate this, it remains only for me to sum the reciprocals of the primes in this interval. Now, I must have mentioned in both of my previous talks that Euler proved in the mid-18th century that the sum of the reciprocals of the primes diverges. And in fact, he had a better theorem than that. And the better theorem is that if you sum the reciprocals of the primes up to some level t, then this is log t. Since I'm writing this at the blackboard, I'll use my more traditional log. In previous lectures, I used ln. It's the same function. OK, it's log t plus a constant plus something tending to 0. And this constant can be written down explicitly in terms of Euler's constant and a certain infinite sum. So here's a theorem of Euler. Let's apply that theorem to estimate this sum here. It's x times. So what would this theorem tell us? Let's do the summation x to the 1/2 less than p less than or equal to x 1 over p. OK? So that's the sum at t equals x minus the sum at t equals square root of x. So this is equal to log x plus b. That's the sum at t equals x, minus the sum at log square root of x minus b. That's the minus the sum at square root of x, plus a small error that tends to 0 as x tends to infinity. The two errors add up to still something small. So you see the plus b and the minus b cancel. And what kind of algebraic simplification can we get for these two terms? Does anybody know? Anyone taught pre-calculus recently? OK, so the log of square root of x is 1/2 log x. And so the log of that is the log of a half plus log x. So the log x's cancel. And all you're left with is minus log a half. Minus log, that's log 2. So this is equal to log 2 plus little o of 1. So what we're getting here for this deal here, that's multiplied by x. So we get that psi x to the 1/2 is equal to x minus x log 2 plus little o of x. So we can combine the first two terms and get that this is equal to 1 minus log 2 times x plus an error that's small compared to that. Now the log of 2, the natural log of 2 is about 0.693. So if I subtract that from 1, I get 0.307 approximately. And so I'm saying about 30.7% of the numbers ought to be there. Did I get 30.7% of the numbers? I got 46%. OK. Slow convergence. There was an error after all. Two errors, an error caused by removing integer part signs, and another error in applying Euler's theorem about sum of reciprocals of primes. Actually, this sharper form of the theorem is really due to Mertens in the 19th century, not to Euler. Okay, so here we have a result then. Let me erase this numerical work, that psi x to the 1/2 is asymptotically a constant times x, where this twiddle sign just means if I take the left side and divide it by the right side and let x tend to infinity, the limit is 1. The two functions are asymptotic to each other at infinity. And so I've just sketched for you how one goes about proving this. Now, this same kind of argument would work if I replaced this exponent 1/2 with a larger number, like if I replaced it with 0.6. The same kind of argument would work. But if I replaced 1/2 with a smaller number, say 1/3 or something even smaller than that, then this argument gets a lot more complicated. Essentially what we're doing is we're doing an inclusion-exclusion. We're excluding multiples of these primes. There is no number that's less than or equal to x and divisible by 2 primes in this range. Because as soon as you're divisible by 2 primes in this range, your product is already bigger than x and it wouldn't be counted at all. But once you start dealing with smaller primes, you have to start worrying about that, and it becomes a big mess. Well, this has been studied. And in fact, there's a solution to the problem. And it generalizes this result that we just worked out. It's a theorem of Dyckman from, I think, the 1920s. And Dyckman proves that psi x to the 1/u is asymptotically rho of u times x, as x tends to infinity. Here, u positive is fixed. So rho of u is a positive continuous function of u. Now, there are certain ranges for which rho of u is absolutely trivial. For example, all I said was u is positive. Consider the case where u is between 0 and 1. If u is between 0 and 1, then the reciprocal of u is bigger than 1. And so I'm looking at numbers up to x, all of whose prime factors are less than or equal to something which is even bigger than the number. That's all the numbers up to x. And so rho of u in that case is 1. So what we have is that rho of u is equal to 1 for 0 less than or equal to u less than or equal to 1. By generalizing this argument here for the exponents between 1/2 and 1, in other words, for the u's between 1 and 2, we can get an exact formula for rho of u in that range. Rho of u is equal to 1 minus the natural log of u for 1 less than or equal to u less than or equal to 2. Once u gets beyond 2, there is no simple formula for what rho of u is. However, there's a simple definition of this function outside of number theory, but inside another subject, namely differential equations. Rho is the solution to a differential delay equation. Rho satisfies this differential delay equation. Rho prime of u equals minus rho of u minus 1 divided by u. It's an unusual differential equation because it depends upon the function at another argument. So this is known as a differential delay equation. Okay, you can integrate this and write rho in terms of an integral, but whatever. Anyway, by studying this function, this is enough, by the way, to define the function rho. I don't even need this bottom line here about being 1 minus log u. That's a corollary of this differential equation and the fact that it's initialized to be 1 on this interval. I'm just integrating 1 over u to the next interval. So this is enough to define rho, and let's look at its graph. Okay, let's get a visual picture of what the function rho of u looks like. So it's defined for, here's the u-axis, and Here's the interval 0 to 1, and its value is 1 on that interval. Okay, that's simple. And now let's go over to 2, and at 2, it's this 1 minus, so here it's about 0.307 at 2, and then it decays to 0. It's relatively smooth. It's not an analytic function because it's analytic on each integer interval from n to n plus 1. It's analytic, but where it's glued together, it's not. So it goes to 0 monotonically, rapidly. How fast? So a Dutch combinatorialist and number theorist has studied the rate at which rho tends to 0. This is De Bruijn. And what he proved is that rho of u is approximately u to the minus u. That's about how fast it goes to 0. So this can be made precise. The log of this is asymptotically the log of that. So there's an error, there's a finer approximation, but let's take this as a poor man's or a poor woman's rho of u, just u to the minus u. Okay, now this is a very interesting function, and you can see it's connected to smooth numbers. Now you might say, well, I'm not too interested in smooth numbers, and so therefore I'm not too interested in your function rho of u. Suppose you have that attitude. Yeah. Okay, well let me show you why you should be interested in rho of u, even if you're not interested in smooth numbers. I'll show you two different ways, other than smooth numbers, where this function comes up. Okay, so suppose what you like is group theory. And suppose you like, what's the most simple thing in group theory is permutation groups. Okay, so let's look at permutations on n letters. You have a permutation on n letters. You know that this can be written as a product of disjoint cycles. Okay, well let's say a permutation is smooth if all of the cycles have small lengths in this unique decomposition. Okay, so how many permutations on n letters have the lengths of all the cycles being less than or equal to n over u? Well, it's some certain positive constant times n factorial. And what is that positive constant? It's rho of u. Okay, well, group theory, permutations, that's pretty close to number theory. Say, let's get out of this discrete math stuff. I'm a probabilist. Okay, well, let's look at probability theory. Let's take a infinite sequence, x1, x2, x3, of these are uniform random variables on 0 to 1. Uniform random variables on 0 to 1. And they're independent. Now, what probabilists like to do is they like to sum independent random variables, but I'm going to be opposite of that. I'm going to multiply them. Okay, so let's let yk be the product of the first k of these random variables. Okay, so now let's look at the sequence of y's, y1, y2. So I get longer and longer products of these random variables. So clearly, the y's are getting smaller. Because if you take this and multiply it by another number, which is between 0 and 1, it only makes it smaller. So these y's are monotone, non-increasing. So let's look at the gaps. In fact, let's look at this new random variable. Let's let z equal to the maximum of all the gaps between consecutive y's. The max of y k plus 1 minus yk for k equal 1, 2, and so on. Maybe I should start it at 0 and let the y sub 0 just be 1. I think I need to do that. So it's just a constant 1. And now you can ask, how big is this maximum gap? So what you could say, what is the probability that this maximum gap is less than or equal to, well, it's going to be some number in the interval 0 to 1. So let's say it's less than or equal to v. This is not a simple probability problem, but it's not too hard either. It's relatively elementary. You can work this out, and it works out to this. Same function. Okay? So that's why I claim that even if you didn't like smooth numbers, this function rho is here to stay. It's a solution of several different problems, and if you didn't see it in one context, you'd eventually see it in some other context. Okay, but now I'd like to convince you that smooth numbers are useful, that they're here to stay, that you can't get around them. And I'd like to announce to you a theorem which is a little bit hard to process. Let me give a definition before I tell you the theorem. Perhaps I can record some facts that we learned here. We have psi x to the 1 over u, asymptotically rho of u times x as x goes to infinity, and rho of u is about u to the minus u. What I'd like to try to define now is the concept of when a certain finite set of integers is multiplicatively dependent or multiplicatively independent. So just like in linear algebra, it's easier to describe linear dependence, I think, than it is to define linear independence. Do you agree with me? Linear dependence is there exists something, and you can demonstrate there it exists, a linear dependency. But for the definition of linear independence, you have to put it in negation of that. There doesn't exist something. Or the only way to write it is whatever, you know the definitions. Anyway, multiplicative independence and dependence is almost the same. In fact, it is exactly the same if you view it that way. So we say that, say, n1, n2 through nk, these are, say, positive integers, are multiplicatively dependent if there are integers a1 through ak, not all 0, with the product n1 to the a1, n2 to the a2, nk to the ak equals 1. And if they're not multiplicatively dependent, then they're multiplicatively independent. Okay, this is exactly the same as what you already know from linear algebra. You just take logs. So this equation here, this product equals 1, if I take logs, it's just saying summation ai log ni equals 0. And so what this is saying is that the logarithms of n1 through nk are linearly dependent over the rationals. Here I said integers, but you could clear denominators if you wanted to. So this says that the log n1 through log nk are linearly dependent over the rationals. Now I claim that there's a simple criterion for recognizing a multiplicatively dependent set of integers. So for example, let me give you an example, a numerical example of some integers that I am sure are multiplicatively dependent. In fact, why don't you give me some integers? Would somebody like to give me a random integer between 1 and 100? 23. Okay, that is not multiplicatively dependent as a singleton. It's not the zero vector. The log of it isn't 0. Okay? Someone else give me another number. 26. Okay? Still independent. Somebody give me another number. 65. Still independent. Getting close. Somebody still independent. Somebody give me another number.
52.
Ah, thank you. I have some plants here in the audience. Okay, now they're dependent. I can tell that they're dependent. Okay, I'm not going to use 23, but I will use the next 4 numbers. And I can tell that they're dependent because look at the primes that are involved in these 4 numbers. The primes involved in 26, what are they? 2 and 13. The prime in 65, 5 and 13. In 10, 2 and 5. In 52, 2 and 13. So between these 4 numbers, how many primes do you see? 3 primes. So in some sense, what I have here is 4 vectors in a 3-dimensional vector space. And they have to be dependent. In fact, we can even, instead of using logs, there's another way of viewing this. We can create exponent vectors. So every integer has a prime factorization. And so let's let the exponent vector for 26 be 1, 0, 0, 3, 5. And this corresponds to 26. And 65 will be 0, 0, 1, 0, 0, 0. Might have too many zeros here. This 1 is supposed to correspond to 2, 3, 5, 7, 11. Too many zeros. I'll try to explain this better in a second, and maybe it'll become clear as I write these down. Okay, here I've written down vectors with 6 coordinates each time. What does the first coordinate stand for? It's the exponent on 2 in the prime factorization. The second coordinate corresponds to the exponent on 3. None of these 4 numbers are multiples of 3, so all 4 of these vectors have a 0 in the second place. Now the third coordinate corresponds to 5, and the second and the third numbers have a single 5 in their prime factorization. So you see a 1 in that place. There are no 7s or 11s in these numbers. There is a 13 in the first, second, and third number. So you see 1 in the 6th place in the first, second, and third numbers. Okay, so what is my vector space? My vector space consists of 6 tuples that have to be 0 in the coordinate for 3 and the coordinate for 7 and 11. That's a 3-dimensional subspace of R6. And I have 4 vectors in it, and they have to be linearly dependent. In fact, we can see, can we write down a linear dependency? I don't know. It's too hard to do it. So sign up for homework. So anyway, let me describe the theorem and show you what this has to do with smooth numbers. So here's the theorem. This is again a theorem in probability theory. It's due to me from a few years back. Suppose I give you integers chosen at random in the interval from 1 to x, independently. So let n1, n2 be independently chosen random integers in the interval 1 to x. Now I'm going to keep on choosing these integers just the way we did until they become multiplicatively dependent. And I'd like to know the stopping time for that problem. So let's let t of x be the random variable which is the stopping time for the chosen integers to be multiplicatively dependent. The question is, what is t of x? So before I state the consequence of this theorem, let's think about it for a second. I didn't say, since the integers n1 are chosen independently, it means it is possible to choose the same integer twice. Okay? And if you happen to choose the same integer twice, they're definitely multiplicatively dependent. Okay? So how about that? How about just that? How about choosing the same integer twice? You ever heard of that problem before? Or do I have to go around asking how many people have birthdays in January or February? It's the birthday paradox from probability theory. Okay? What does that say? It says that if you just want to get a match, then when is it likely that there'll be a match? The two will be exactly the same. When you get to be a large constant times square root of x. If you choose n1, n2 up to nk, where k is large compared to the square root of x, k divided by the square root of x is large, then it's overwhelmingly likely that two of the ni's will be equal. And if k is a small number times square root of x, it's unlikely the two will be equal. Okay, so whatever this t of x would be, it'll be smaller than square root of x, because there are going to be many more ways to be multiplicatively dependent than just getting a match, which is a very cheap way. So in fact, the answer to this question is the following. Then almost surely t of x, or you could say the expected value of t of x or whatever, is this function of x. It's e to the constant square root of 2 plus something going to 0 times the square root of log x log log x. That's what it is. That's the answer to the problem. Now, you can ask, how does this function, not a very pretty function, I'll admit, but that's the answer, so what can you do? How does this function compare with square root of x? Is it bigger than square root of x or smaller than square root of x? How do you make that comparison? Well, you write square root of x as e to something. The square root of x is e to the 1/2 log x. Okay? So compare the exponents. How does 1/2 log x compare with this exponent? Well, there are lots of stuff going on here in this exponent. What's the most important stuff going on here? It's the square root of log x is the most important. The double log is less important, and the square root of 2 is even less important than that. So how does square root of log compare with log? It's smaller. So square root of x is quite a bit bigger than this. Okay, well, what about x to the 1/10? I take x to the 1/10, the small power of x. That's e to the 1/10 log x. And so at infinity, this is still smaller. This is smaller than any root of x. It's a so-called sub-exponential function of log x. But it's higher than any power of log x. Okay? Now, why should this theorem be true? How might you go about proving this theorem? Well, there are two sides to proving this theorem. The first side is to show that if you replace this little o1 with a plus epsilon, then almost surely in that sequence that you've chosen up to that point, you'll find a multiplicative dependency. And the other side of the theorem is if you replace this little o1 with a minus epsilon, then almost surely the set you've chosen is multiplicatively independent. Now those two theorems are separate theorems, and one is easy and one is hard. Okay, but let me show you the easy one and how the easy one works. The easy one is the one with the plus epsilon, to show that once you get up to plus epsilon, so that the claim is that if you have n1, n2 to nk, where k is e to the square root of 2 plus epsilons, plus a small quantity, log x, log x. These are almost surely multiplicatively dependent, which is 1/2 of this theorem. So what is I'm not going to give you a detailed proof of this, but what is the idea of the proof? What we're going to do is we're going to say, okay, here we're choosing these numbers at random, completely at random. They could be anything. They could be a number like was first suggested, like 23, which is a pretty large prime in the range, or they could be a number, which is all small prime factors. Some of these numbers, some of these ni's might be smooth, and some of them might be, in the words of Ram Murthy, crunchy. Okay? Not smooth. Okay? Suppose, just to simplify life, I throw away all the numbers that are not smooth. I just keep the smooth ones. In fact, let me tell you exactly how smooth I'll keep them. I'll let y, for the y smoothness, I'll let y essentially be the square root of this function without the little o of 1. Y is equal to e to the square root of 2 over 2 times the square root of log x log x. And I'll just keep numbers that are this smooth. What is the probability that I'll be keeping a number? What is the probability that I'll be keeping a number? Well, that's a problem we sort of looked at back over here. The probability I'll be keeping a number is psi x of that y divided by x. Now this theorem of Dyckman that I told you about at the beginning of my lecture is only for u fixed and x tending to infinity. But here, if I do this, the u is not a fixed function of x. It's not a constant. The u is going to be log of this divided by the log of that. So it's going to be square root of 2 times square root of log x over log x, log x. If you work that out, that's what the u turns out to be in this theorem. And so we cannot apply Dyckman's theorem. We can't do it. However, in the early 80s, in a paper I had with Canfield and Erdős, we showed that the estimate, putting together that rho of u is approximately that we had an estimate like this, even when u was as big as this. And so using this theorem of Canfield, Erdős, and myself, you can say something about the probability of one of these numbers coming along being y smooth. And in fact, this ugly, strange function is chosen so that this probability is just about 1 over y. Okay? So the probability, some ni, is y smooth, is about 1 over y. And how many numbers am I choosing? I'm choosing about y squared numbers. So how many y smooths should I expect to see? If I choose y squared things, and each time probability of success is 1 over y, I should expect to see about y successes. So we'll see y successes, y smooth numbers. Here again, what is the dimension of my vector space? The number of primes up to y. How many vectors do I have? Y. I have more vectors than the dimension of my vector space. They're dependent. They're multiplicatively dependent. And so this relatively easy theorem that depends upon this result of Canfield, Erdős, and myself proves 1/2 of this theorem. And the other half is a lot harder to do, and I won't subject it to you. But you can see that this theorem, which doesn't mention smooth numbers at all, it's a concept just involving multiplicative independence and dependence, forces smooth numbers on you. Now, another question is, why should you be interested in this theorem? Let me show you why you might be interested in this theorem. There's a related quantity to a related concept to multiplicative dependence and multiplicative independence, which is when a subset will have product being a square. And it turns out if the set is multiplicatively dependent, then it definitely will have a subset of the numbers being a square. Let's say we try to factor the number 1649. Certainly looks like a square, doesn't it? Ends in 49, starts with 16, has a 64 in the middle. It's not a square, though. Let's say we want to try to factor it. What's the square root of this number? About 40. Okay, well, what's 41 squared? Take away, let's call this number n. 41 squared, take away n. Now, 41 squared is 1681, which is how much above this? This is 32 above this number n. Let's take 42 squared minus n. So I'll be adding on 83 to this number, which is 115. Let's take 43 squared, take away n. I'll be adding 85, I'll get 200. Now let's look at the sequence of integers that I'm getting here. I could continue this for a ways if I wanted to, just by taking consecutive squares, subtracting n, get a sequence of numbers. Is this sequence of numbers random? No. I'm telling you exactly how I'm forming them, right? Does this theorem know that? Does this theorem know that we're forming the numbers this way? It doesn't know it. Okay? Maybe we'll find a subsequence of these numbers which are multiplicatively dependent, or even a subset whose product is a square. What's our strategy? Look at smooth numbers. Which of these numbers is the smoothest? 32, it's a power 2. And which of these numbers is the second smoothest? The last one, 200. Largest prime factor is 5. 115 isn't too smooth. It has that factor 23 in it that we saw before. In fact, what about 32 times 200? It's a square. 32 times 200 is 6400, which is 80 squared. Now, why is that interesting? Let us treat this first and third statements as congruences. I'll write the first statement as 41 squared congruent to 32 mod n. And I'll write the third statement as 43 squared congruent to 200 mod n. And now let me multiply together these two congruences. And what do I get? The product of the two left sides is 41 times 43 squared. That's the product of the two left sides. And what's the product of the right sides? It's 80 squared. And so here I have a square congruent to a square mod n. And so what I could say from this is that, well, what is 41 times 43? I guess that's 1763. And what is that congruent to mod n? 1763 is congruent to 114 mod n. So what I have here is 114 minus 80 times 114 plus 80 congruent to 0 mod n. Now, congruences are funny. They're a lot like equations. And if you had an equation, if you had the product of two things being 0, you deduce that one of the two things is 0. Well, congruences aren't that much like equations. However, if you have the product of two things being 0 mod n, it must mean that n has a non-trivial common factor with one or both. What is the common factor? What is the greatest common factor? Let's take the first factor. First factor is 34. What is the greatest common divisor of 34 and n? 1649. Euclid has a method for computing greatest common factors that involves dividing the smaller number into the bigger number, getting the remainder, replacing the bigger number with the remainder, and iterating. You work that out a couple steps, 17. What did we just discover? We discovered that 17 is a factor of 1649. And we did it by a method totally unlike trial division. Trial division was the farthest thing from our minds when we did this. Working with squares, subtract n, looking for smooth numbers, maybe doing some linear algebra with these exponent vectors to try to get squares. It was so easy here, you didn't even need the linear algebra. And coming up with congruent squares mod n, and then doing a Euclid GCD to find the greatest common factor. This, in a nutshell, is a modern factoring algorithm. This is known as the quadratic sieve. And the quadratic sieve is not a rigorously proved method. But as I said, the numbers don't know that. Okay? You get a sequence, and you assume it's random. You assume it's random. You assume a theorem such as this can be used for it. And as far as we know, it is random enough, and it works. And it factors big numbers. The record size number that's ever been factored with the quadratic sieve is that number in the headline in the New York Times that I showed you 2 days ago, a 129-digit number that was a key to a public key code. Now, one can use this theorem to give a heuristic running time for the quadratic sieve. And this theorem depends on x. The answer depends on x. And so what we need here is a bound on the numbers that appear in this column here. Are these? Yes?
When you're using this, keep going through those squares, presumably you have to give up at some point and say you didn't find any product with the squares. How far do you go?
Well, see, now the idea, I'm leaving out a whole lot, of course, but the idea is that this sequence of numbers is formed in a very regular way. They're the consecutive values of a quadratic polynomial. The polynomial is x squared minus n, starting at x equal to the first integer above square root n. And because of that, you can use a sieve very much like the sieve of Eratosthenes, which detects primes, to detect smooth numbers. So you set this whole thing up as a big sieve problem. You just mark things off and whatever. And at the end of that sieve, you have detected those numbers in this column that goes on for a good long ways, which are smooth. And throw away all the others. And when you have these smooth ones, you create these vectors out of them. And the vectors are easier than the vectors we were looking at before, which I've since erased, because the exponents are all reduced mod 2. Because I'm only interested in even and odd for the exponents, because I'm trying to get a square. And you do this huge linear algebra problem. Maybe it's 100,000 by 100,000. Not trivial, but very sparse, and all the arithmetic is mod 2. And you could create your congruent squares in that way. You find the subset. And I'm not sure I answered your question.
Well, I suppose the question was, certainly, if you do find a factorization, you know you found it. If you don't find a factorization, how do you know?
What I mean is that we don't actually take each of these numbers separately and look at it and spend a good deal of time on it. The smooth numbers are pretty rare, and we don't want to waste time. So the sieve method is sort of an automatic device for picking out the smooth numbers. So for example, this number is divisible by 23. Every 23rd number after that will be divisible by 23 as well. And so we can tell exactly where the multiples of 23 are in this list. And this number is divisible by 5. And we can tell every fifth number after that will be divisible by 5. And we can tell where all the multiples of 5 are. Every other number here is going to be even. So we can tell a lot about where various primes go in the list. And if we think of the list together as a whole, rather than each number individually, we can detect the smooth numbers in very, very little work. We don't actually take it out and divide it and see what's in it. Some numbers are successful, but it's only a minority. Most of them just get discarded. Yes?
Is it simply an accident that the next factor
Right, yeah, so this has the other factor. Right, so of course it's not an accident, because for this product to be 0 modulo n, you have to see all of the primes in n appearing on this left side. So it either every prime in n divides either that factor or that factor. And we'll be successful if the prime factors of n get split up, some here, some there. This is not guaranteed to be successful. If all the primes in n are all in one factor and none in the other, we'll take the GCD and we'll find that it's n. And we'll discover that n is a factor of n. And we won't be very happy about that, because we knew it before we started. So the running time for the quadratic sieve, if you assume that these numbers really are acting like random, is something like this. The reason the square root of 2 went away from this theorem is because the x that's involved is something like the square root of n. And so we get a square root of 1/2 coming out from here, canceling with the square root of 2. Now, there's a better method than the quadratic sieve that has been introduced in the last decade, known as the number field sieve. And the number field sieve is a lot more complicated than the quadratic sieve. And why bother doing something more complicated just to show we're smart? I mean, what's the point? Simple is good when you're running an algorithm. But the reason we do the number field sieve is that the x that's involved is a lot smaller. And if the x that's involved is a lot smaller, so in quadratic sieve, the x is about square root of n. In the number field sieve, it's about e to the log n to the 2/3. And so here in this method, the running time for this, again heuristically, is about this number. You take the cube root of 64/9 and add something that's small. And you take the cube root of log n and the 2/3 root of log n. And that's all up there in the exponent. Now, there are two things that are bigger in this exponent than this one. The log n is raised to a higher power, and this number is close to 2. Well, that's 1. And the most important thing, though, is smaller. Nevertheless, for small n's, this is a smaller function, not a bigger function. And the crossover between these two functions, ignoring the little o of 1, is about, definition of small here, is about 10 to the 125. Okay, so if you want to factor a number that's small, like below 10 to the 125, use the simple method, quadratic sieve. If you want to factor a big number, then you use number field sieve.